that I should get a dv dt. I always have trouble saying that. dv dt pops out somewhere, dA dt will pop out somewhere. It's just a question of, are we going to do this derivative correctly or not? All right, so here we go. My implicit, I'm doing derivative with respect to time, and the left side is the easiest side, right? dv dt. Yay. Equals. Now, 4/3 pi is a constant. It's just going to come for the ride. So I'm just going to write it down right here. 4/3 pi. But the rest of this right here has your variable in it, right? And so you have to look at this as chain rule. You start off like you said, my hand to the 3/2 power. The derivative of my hand to the 3/2 power. 3/2 comes out. 3/2. My hand to the 3/2 minus 1, which is 1/2. Then that's, is everyone following that? I'm not done, but does everyone follow? That's the 3/2 coming out? Okay, times chain rule, the derivative of what's inside. Now look, what's inside, look everyone, real quick, what's inside? A over 4 pi. I know a lot of you are thinking quotient rule right now. Let's just rewrite it like this. Isn't that not the same thing?
Actually, no. Yes, that is the same thing.
That's the same thing, right?
Yeah.
And that's a constant. So when I take the, no, because it's attached to a function. So if I were to ask you to take the derivative of this, it's the same as derivative of this, the constant would come along for the ride, right? So 1 over 4 pi would be here, times, so that came for the ride, and then the derivative of that. Derivative of that. I think I heard it. dA dt. There it is. Voila! That's your derivative. Now, we plug in. Let's check to see what we have, okay? I've erased everything. dv dt is what we're solving for, right? Yeah. Constant, 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 constant. I'm going to need to know what A is. I'm also going to need to know what dA dt is. Do I know what dA dt is? Yes. So there is a problem here. I don't know what the area is. So I need to go figure it out. So now I go back to my fixed situation. I have my sphere sitting there. In that instant in time, my sphere had what? What was that information I had? Volume was 36 pi cubic feet. I need to somehow figure out what the area is. Right? From this? Right? Okay, so let's just take a look back real quick here. Didn't we come up with an equation that relates A and V together? Didn't we generate that ourselves? We were very proud of ourselves for that, right? So if I sit here and I plug in V is 36 pi right here into this equation, see, notice I'm working with the original equation. I'm not working with the derivative of it. If I plug 36 pi in here, then the only letter in there left is an A. And you should be able to solve for that, right? So let me do that. I'm going to go to this equation. I'm going to replace the left side with 36 pi. You following me? Okay. Left side is 36 pi equals, yes, this is going to look this bad. 4/3 pi, A over 4 pi to the 3/2. Now, if I were doing this, if I were looking at this, which I am doing this, hey, I would see that the pi's are going to go away right away. Both sides. Those are gone. I don't like those. Divide by pi, they're done. I'm going to multiply both sides by 3/4 to get rid of the 4/3. I multiply this side by 3/4, this side by 3/4. Didn't we do that earlier? Yeah. We did. So this side by 3/4, it goes away. This side by 3/4, we get 27, don't we? Now I need to get that A out of there. The 3/2 is a problem, isn't it? So what I'm going to do is what we've done in the past when we have like square roots, we can square both sides of the equation. Here what I'm going to do is I'm going to raise this side of the equation to the 2/3. And I'm going to raise this side of the equation to the 2/3. Now why in the world would I do that? That's right, because you use the property of something raised to a power, you multiply those powers. And if I multiply a fraction by its reciprocal, I just get a 1. And that's going to be this to the 1 power, so it's just a over 4 pi. Was I being truthful when I told you it's going to get a little harder? Okay. On this side, though, what does that mean? What does 27 raised to the 2/3 mean? There's a couple ways you can look at it. You can look at this as being 27 squared and then take the cube root, but you can also do the cube root of 27 first and then square the answer. These mean the same thing. All of these mean the same thing. This is the power, this is the root. You can do them in any order you want. I'm going to do the root first because root 27 is 3. Squared is 9. So this side is 9. Almost have a. Multiply both sides by 4 pi. 36 pi. It is only coincidental that the area is 36 pi and the volume is 36 pi because they are not the same units. This is 36 pi square feet versus 36 pi cubic feet, totally different things. We good? We're almost to the answer. All right, here's where we were, right? I circled this in red because I didn't know what it was. Now I know what it is, right? It's 36 pi. So I'm going to come back to this and I'm going to solve. I'm also going to cancel these 3's. And this 2 and this 4 are going to become a 2. Is that all right? All right, let's plug in. dv dt is equal to, I have a 2 pi. In here, a, which is 36 pi, over 4 pi, raised to the 1/2, times 1 over 4 pi, times, what's dA dt? 20. Hey, what's this in here? That's 9. What's 9 to the half? That's square root of 9? What's square root of 9? 3. That's a 3 right there. Right? This whole thing is a 3. No, the pi's canceled. Pi's just canceled out. So I have, let's see here. This thing's going to become a 3. Are we good with that? That's gone with that pi. That pi's on the bottom, that pi's on the top. And let me do a little more. How about 20 divided by 4? 5, and then I still have a 2 out here, don't I? So I have a 2 times a 3 times a 5. The answer is 30. Look, all this in here is just arithmetic, isn't it? At this point, this is all just arithmetic going from here to here. 30. Yep. After you cancel everything, turn that into a 3. You'll have a 2, and then this is a 3, and then 20 divided by 4 is a 5. And now I'd like to know what units that is in. No, it's dV dt. So cubic feet per, it was second in this problem also. So our answer is 30 cubic feet per second. It's a little harder when the formulas you need don't exist and you have to create them yourself, right? So I was thinking about this last night or the night before. I remember when I first got into graduate school and started doing, did I tell you about those sessions that I used to have to do in graduate school? Yeah. I think it was my other calculus class. If you ever do graduate school, a lot of schools offer what's called being a TA, a teaching assistant. And so like you have different jobs on campus, and that's like instead of going to work, that was my job, and they pay you. It's not much, but you can survive, I guess. And so my duties were I taught like 2 like test prep courses. They were like courses that were people who were coming into college and weren't ready for like college algebra. It was like courses to get them ready for that course. So I taught like 2 of those, and then I worked in the tutoring lab a couple of hours a week, about 10 hours a week, and then I had to do these calculus sessions on Fridays. So basically what would happen is, you know how you come to class twice a week for an hour, 40 minutes? The university, they would do 2 times a week for an hour, 15 minutes, and then they would go to a Friday session for like an hour. And what would happen is I would walk in there and I'd be like, I'm not their professor, I'm just some guy who was in the math department. I walk in there, I'm like, any questions? That's it, like that's what I would do. And people would ask questions on homework problems, all right? So I had to walk in there and be able to answer any question out of the book, right? From a Cal 1 class. This section was the most intimidating section that I ever had to help anyone with, because every problem is different. Every problem is different. And so you have to understand what you're doing in order to feel comfortable with this. You can't be like, okay, I can do a circle problem as long as it's radius and area. No. You have to be able to do any problem where you can relate 2 rates together. This is a good example of this problem of how it's not cut and dry. We had to go and attack those 2 equations and manipulate them to create our new equation. And this is not pretty, but if we follow the rules of calculus, we do the derivative correctly, we use the chain rule correctly, we will result in a final answer that's correct. All right, so, and I think you'll see what I mean by the variety of questions when I get to this next one. This is the plane flying overhead problem. And this will probably be the last one we do. Well, we might do one more, let's see. Just depends on how fast we go with this. And let me reassure you also, when I was in your shoes doing Cal 1, I in no way, shape, or form knew it the way I know it right now, okay? It probably took me being in graduate school for me to understand Calculus 1 correctly, because it just takes that much time. That's why I have a problem when you go to the tutoring lab and there's someone in there to help you and you're like, well, what math have you taken? Well, I just finished Cal 1 with an A. Okay. That doesn't mean a lot, okay? That doesn't mean, because I guarantee you that if you take someone who just took Cal 1, they could not do every problem in this section. You know what I'm saying? You have to build up years and years of doing math before you can be comfortable with it. Why am I telling you that? Don't feel uncomfortable if you feel uncomfortable with this. Like, don't be like, well, I can't do engineering. But you have to be willing to try and put in the time and the effort. I mean, that's the important thing. All right, plane flying overhead. So the idea here is that you've got this plane. There's a radar station on the ground. The plane's flying by, right? And it goes past you. And just imagine that you were holding a rope that was tied to the plane. As it goes over, that rope is pulling out of your hand, right? Just shredding your hand. And what we want to know is at a specific instant, how fast is the rope coming out of your hand? How fast is the distance between those 2 changing? There's the word problem. A plane is flying horizontally at an altitude of 2 miles and a speed of 600 miles per hour. The plane is headed directly over a ground-based radar station. At the moment, the plane is 6 miles from the radar station. How fast is the distance between them changing? Instant. General. What do we want? Or what do we know?
We know the height and the speed.
And what do we want? Okay, I heard that we know the height, right, of the plane. 2 miles, and that's never going to change.
Yeah.
in the problem, right? Unless we shoot it down, which is why we have the radar on the ground to begin with, right? So that too is obviously going to play a role in the problem, but when we were looking at what we know and what we want, these always had like derivatives, didn't they? So although 2 is important, I'm not quite sure it's quite going to fall into the no category yet. The speed of the plane, right? 600 miles per hour, that's a speed, that's a derivative. I think that that's probably in my no, isn't it? I'm going to write it down, 600 miles per hour. What I don't know yet is what to call it. D what, right? Because I don't even have a picture yet that goes with the situation. I don't have a variable for that picture. So maybe I should work on a picture. Maybe I should work on a picture. And I think I'll do a general picture first. I have the ground, and I have a point on the ground. I have a plane that's flying overhead that could be, in general, at any point, arbitrarily, right? As long as it's 2 miles high, this plane could be at any point above here. Right? So let me just place it wherever I'm not going to put it right on top because it's going to be kind of boring. Let's move it to the side a little bit. Let me just put this plane right here. Radar plane. I know for sure, no matter what, from here to here is 2 throughout the whole problem. So even though I'm in my general picture where things are changing, that doesn't change. Do you agree? I'm interested in the how fast the distance between the 2 are changing, right? I need to label that on my picture. When I say distance between the 2, I'm talking about the straight line distance between 2 points. I am not talking about, if you look straight down from the plane, how far away it is on the ground. All right? I'm talking about if you draw a straight line from here to here, what is that distance? And that is changing, and if I let that plane move, that purple thing is changing, isn't it? So I better give it a variable. What do you want to call it?
H.
I'll call it H. I'm okay with H. Yes? Is 600 dH dt? No. But what we want is dH dt. Do you agree with that? I want to know how fast this distance is changing. So I want this. When do I want this? At what 6? At the moment the plane is what? 6 miles from the radar station. So when the distance from here to here is 6, right? What are we calling that? When H is 6. Right? I want to know how fast the distance between them is changing, what the rate of that change is, at exactly the moment that the distance is 6 miles. Okay, so things are starting to come together here, you think? Yes? I still need to work with that 600 though. Does anyone see what geometric shape I could use for this to try and come up with an equation? A triangle? Okay, let me try and draw a triangle real quick. A right triangle. Yes? The speed of the plane. That's the speed of the plane. Where is that on my picture? Isn't that this dot is moving that direction, right? It's moving at 600 miles per hour, isn't it? It's flying horizontal. Yeah, there's a little tilt to that, sorry. It's supposed to be horizontal. So I know that this dot is moving 600 miles per hour that way. Would you agree with me if I said that this dot down here is doing the exact same thing? As the plane moves, this point moves at 600 miles per hour horizontally. That dot right there will also go 600 miles per hour in my picture. Yes? Agreed? And if I called the length from here to here x, then you can look at this point right here as like being an anchor point. And what's happening is this distance right here is growing, isn't it? X is growing as time goes by. How fast is x growing? 600 miles per hour. I've actually created the variable that will represent that change. So I can call that up there what? dx dt. And at this point, you can try to go for the equation. Unless you want to do the instant in time. You want to do that? Let's do the instant. I always ask you questions and don't let you answer, right? Do you want to do that? Yeah, we'll do that. At the instant in time, what can you tell me?
I guess the hypotenuse would be 6.
Yeah, h was 6, right? So I know this is 6. If I know two sides of a right triangle, can I determine the third?
Yeah.
Absolutely. Now, I may not need it, but let's just keep in mind that this down here is x, isn't it? And x actually has a value that I don't quite know unless I go work it out. But I can find it if I need to. What is the equation that is somehow going to relate h together with x? Any equation you can come up with. Okay, what is that? How does that thing go? A squared plus b squared is c squared for a right triangle. A squared plus b squared is c squared. So for us, we really mean this squared plus this squared must be this squared. So let me write that down. X squared plus, can I write 2 squared? Yeah, 2 is always, right? 2 is always 2 in this problem, right? That never changed. So I can write 2 squared, that's 4. Must equal h squared. Yeah. There's your equation. Has x and h in it. Great. I'm going to differentiate it now. With respect to time. Derivative of x squared. dx dt. We need that, don't we? dx dt needs to be here, because it's here. Plus 0, because derivative 4 is 0, equals 2h dh dt. And we can kill off the 2's. So we have our formula. X dx dt equals h dh dt. Let's inspect this real quick, make sure we have everything we need. Do we know x? Not directly, right? Not directly, we don't know what x is. So I'm going to have to go find this, right? Do I know dx dt? Yes, 600. Do I know h at the moment in time? 6, yes. dh dt, that's what I'm trying to find. So there's only one thing I don't know, and that's x. So I come back over here to this, and I use the Pythagorean identity that says that x squared plus, what, 2 squared must be 6 squared? Root 32. So subtract 4 on both sides. Take the square root. Root 32 is x. Questions? I'm ready to put my answer in here. All right, here we go. Writing this down. X is, we just said, root 32. dx dt is 600 equals h, which we said was 6, and dh dt is what I'm solving for. I could divide both sides by 6 right now and write it a little different. I'll write 100 root 32 instead. dh dt. What are the units? We'll get a decimal here in a second. What are the units on this? H is your hypotenuse, right? It is speed, but let's just do with the units just so everyone's clear on it. H is this distance, right? What are we measuring distances in? Miles. Time in this problem is measured in hours, right? Because miles per hour was given here. So this answer should also be in miles per hour. And on your calculator, someone can do that for me? 100 times root 32? That's good. So at the moment, exactly at the moment that this plane that is 2 miles high is 6 miles away from the radar station, it is moving away from the radar station, straight line distance, at a speed of 565.6-ish miles per hour. Question? Okay. All right, we have 15 minutes. That should be enough time for us to do the last one. We're going to come back next class. We're going to do more of these. What I hope to do next time is to provide you with a couple of basic ones. Maybe we can do that group thing where y'all go on the boards. But I'll give like each group like a different problem. That would be, yes? Do y'all think y'all would want to do that? Or you just want to show, like watch me do them all day?
I was out, but the 100 square root of 32 equals HDT. How'd you get to that? Where'd you get the 100 from?
Oh, I just divided both sides by 6.
Okay.
So 6 here, 6, no 100,
Okay.
or 6 into 600. All right, now I like this next problem because it's probably the most practical when it comes to a plane flying overhead. And that is, it's the same scenario. You have a radar station on the ground, but this time this radar station is actually, the radar is actually tracking the plane across as it goes overhead. All right, so when this thing's going over, instead of talking about the distance between the plane and the radar station, we want to know how fast this angle, we call this an angle of elevation, how fast it's changing. So a good analogy of this is, I don't know, I've never been to like a NASCAR race, okay, but I can kind of imagine what would happen if I was standing right there next to the track and these cars are going by real fast. You see the car way down there, right? And you start following it and your head's turning, right? But as it gets closer, you have to turn faster to keep up with it. And then as it gets further away, you don't have to turn your head as fast. So it's kind of like, you know, and you just, you like that? This in here, in this middle range, right? You have to speed up to keep up with it. But as it gets further away from you, you don't have to turn your head as fast to keep up with it. Same thing here. The radar station's looking at the plane. When it's real far away, it's just tracking it real slow. But as it gets closer and closer, this angle starts to speed up. And you can see it in here. Watch the angle here. When it starts in the problem, like 7, 8, 9, 10, 11, and look how fast it starts counting. And then it's going to start to slow down. You see that? Yes? What we want to know is at a specific instant in time, how fast is that angle turning? If you're ever going to shoot a plane down with a rocket system, right, you've got to know how these, I mean, right, like you look at our like defenses on aircraft carriers, and they've got all these guns on the side that are all tracking whatever's coming in, and they're shooting bullets at them, and they're, you know, going to predict where the plane's going to be and shoot the bullet so that the plane hits the bullet. They both meet at the same place, right? You know what I'm saying? You aim at a plane right there and you start shooting it. By the time your bullet gets there, it's over here, right? So you need to know how fast things are turning in relation to one another. This is a very basic, primitive example of that sort of thing.
What you do with the scope is like kind of...
You lead it, right? It's the same thing. And that lead has something to do with calculating the speed of the object. That can tell you how fast you need to turn to keep up with it. That sort of thing this is a very basic example of it. All right. Let's try and set this up. Let me pause this.
So you're teaching us how to shoot down your drone?
Yeah.
It's got like anti-defense.
You're still not going to do it. You still wouldn't be able to do it.
If I see that sucker over my house, you know, shots are going out. We're going to create our own drone.
I'm excited. I get to take that thing out this weekend and
How many hours have you put into it total?
flying time, or just
Like making the 1500 or something?
those videos and stuff. I don't know. A lot. It's a hobby.
Math isn't your hobby.
Like flying your little drone is part of your hobbies too?
That is my hobby. That's what I'm saying. That's my new hobby. I'll have that for a year or so, and I'll go to a different hobby.
Most people would just do crafting, but I guess no.
I also do basket weaving. All right, look, let's get this done. We only have 10 minutes. So look, what do we know here? Same problem, right? We know the speed of the plane, 600 miles per hour. And I'm going to kind of predict ahead of time that we're going to call that dx dt, because we're going to probably go off the same picture for the most part. So let me get my general picture drawn here for you. Wow, that's not straight. That's not level. I never write level, do I? Y'all ever notice that? 2 from here to here is x. If I draw that triangle again, do I need h this time?
Well, if we're going to have to solve for x again.
Okay, if we have to solve for x, we would need it. But what are we interested in? The angle. I better put the angle in there. The angle I'm going to put right in here, I'm going to call it theta. And so I'm interested in the rate at which theta is changing, right? How fast is theta changing with respect to time? I want d theta dt. When do I want it? At the moment the plane is 6 miles from the radar station. No, at the moment the plane is 6 miles from the so not x, it's the hypotenuse again. So it's when h is 6. So I'm going to need to label it h. Okay? I was trying to avoid it because I didn't need, and nothing in the problem told me I needed that, right? But now I actually need it because of that, 6 miles. Any questions on the picture? Still 2 miles high. X is still moving across this way at 600 miles per hour. H is changing, right? H is changing as time goes on, but so is theta. Theta is changing as time goes on. What's my instant picture look like? This is still 2. What? 6 up here, right? And if you know that that's 6, we already solved in the previous problem that this was 32, or root 32. Equation. We need to get theta and x connected to each other. Theta and x. Theta and x. Trig functions. Trig functions. SOHCAHTOA, right? So you could use, let's look at this. Sine of theta is opposite over hypotenuse. Sine is opposite over hypotenuse. Is that going to connect theta and x? No. Cosine is adjacent over hypotenuse. Will that connect x and theta together? Yes, it would. Cosine would. You'd have adjacent over hypotenuse. But it's going to include h in it, isn't it? And so I could do it, but wouldn't it be better to use this side because that's fixed at 2? So is there a way to get theta and x connected by using this side? Tangent theta. Tangent theta is opposite over adjacent, and that's it. I just write it down. Tangent theta, according to my picture, is the opposite side over the adjacent side. And I can differentiate that, right? Yep. With respect to time. What's the derivative of tangent theta? Secant squared theta. Times d theta dt. Good. Got to have the chain rule, right? Derivative of tangent of my hand is secant squared of my hand times derivative of my hand. Derivative of theta is d theta dt. What if you would have forgot that? Then you would never be able to solve for it, right? Because it wouldn't even be there. Equals. Other side? How would you do that? The x is on the bottom.
Also,
How would you do the derivative of this?
for the first time to the second, so it'd be x.
Are you doing quotient rule?
Yeah.
You could do quotient rule.
Or you could bring that up to the top.
Or you could rewrite this as 2x to the negative 1, right? And then take the derivative of that. That's what I'm going to do. So the negative 1 pops out. It becomes negative 2. X to the negative 2. Right? Negative 1 pops out. Then you subtract 1 from this. Becomes negative 2. But then times dx dt.
Where does the dx come from here?
Chain rule. Yep. You have my hand to the negative 1. Negative 1 comes down. Then derivative of x with respect to t is dx dt. See, it's not 1 anymore. It's just, because we're differentiating with respect to time. All right, let's see if we have everything we need. Let me start on this side. dx dt. Yes. Do I know x at the moment in time? Yes, it's root 32, isn't it? Yes? Do I know d theta dt? No, but that's what I'm solving for. Do I know secant theta? No, I don't know what theta is, do I? But if I come back to this picture over here, because now I can fix everything in time, this is theta, right? What is secant by definition? Secant is what over what? It's in terms of sides. Which side is it? Secant is, it's the reciprocal of cosine, isn't it? Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. So 6 over root 32 is secant theta. Agreed? Secant theta is 6 over root 32. But it's squared over here, which is fine. I can square that. See, I didn't have to solve anything. I just used the triangle to figure out what that was. So I'm ready. I'm going to plug everything in. I'm ready, and I'm ready to get out of here. Secant theta, 6 over root 32, squared, times d theta dt, which is what I'm solving for, equals negative 2 times, now be very careful here. What does x to the negative 2 really mean? 1 over x squared, right? That's what that really means? So I'm going to write it that way. That's 1 over, what was x? Root 32 squared. Do y'all see that? Then times 600. Cleanup time. This is going to be like perfect timing. Square that, we get 36 over 32 d theta dt equals negative 1200 over 32. I just put negative 2 times 600, right? I squared the square root and it went away. I'm noticing here that I have 32 on the bottom on both sides. So I can multiply both sides by 32 and they'd be gone, wouldn't they? And then to get d theta dt, I'm just going to divide by 36. So somebody please on their calculator, get me negative 1200 over 36.
100 over 3.
It's 100 over 3, negative 100 over 3, which is approximately negative 33. Is that right? 0.33, whatever. What? Right? Theta. How are we measuring the angle? It didn't say degrees or radians, right? It's always radians unless they specify degrees. It's always radians. Always. Radians?
Which doesn't have a thing.
No. No, it doesn't. but I'm going to put it here, radians per time. What's the measurement of time? Hours. Negative 33 radians per hour. How do you convert from radians to degrees? Do you remember?
Pi over theta equals radians.
You multiply by 180 and divide by pi. So if you want to convert that to degrees,
3.3 times x per over 80 over pi.
1,000
Wait,
negative 1,907.9 degrees per hour. That seems like a lot of degrees, right? But it's per hour. It's per hour, though. That's a long time, right? If I say I turn 360 degrees in 1 hour, that's the minute hand on a clock, right? That's slow. So this is pretty slow, all right? That's not as big as it looks. Okay, what I suggest you do this weekend is work on your homework. I have posted the video solutions to all the problems for 2.7. I would recommend that you look at the first, at least the first 8. Well, the first 6. Yeah, the first 8. I'd work on that this weekend. Have a great day. Sure. Let me turn this off.